All right. Hello, everyone. Welcome back to Comp 2160 Programming Practices. I don't know about you, but I'm really happy that today we have a nice sunny day and it's going to be sort of warm, and especially after complaining about it so much yesterday. So I'm really happy that that's happening. What did I want to do? I want to show you something. So give me a second here. I want to show you something. This is something that I posted to the discussion forum, but I want to show it in class. All right. I'm assuming you all see the same flow for this, like log in and then have to type in a number and then. Do I like it? I consider it to be a necessary evil. Let me say it that way, yeah. I don't know. I do it every single time I log in. Well, that could be. I'm kind of going all over the place. Here's the thing that I wanted to show you. So all the terminal applications that we've been building so far have been quite boring. Like the coolest thing that I think we've done so far is make pass and fail red and green. And then if you're getting to starting to work on the bonus part of this assignment, like using more than red and green, but having many colors show up in your terminal. The long-term example that we've got, I mean, what it prints out right now in terms of like stuff in C is that. Like this isn't cool stuff. It doesn't look very cool. There's a lot behind that print statement. Like there's a lot of code that we put into that and a lot of work that we put into it, but it's not really cool looking. And your experience with the terminal so far might be very much like, this is pretty lame. So I want to show you this. This is a library and an application that's called Terminal Text Effects. This is a Python library, but it's also a program that you can install on your system, and you can pipe output to it and do cool stuff like this, like have it render this in your terminal. I should have installed this before class. I didn't think to do it, but they have all these really neat effects that you can apply to text in your code. So if you're writing programs in Python that are printing stuff out to the terminal, or if you want to do things like pipe LS's output to something like this, you can do it. If you go to this how to use and install this TTE and you go to application usage, they give you this example of you can pipe the output of LS to that program and have it do like all sorts of cool stuff with your output. All this is to say that the terminal doesn't have to be boring. It can be quite cool. It can be quite cool. It can be quite cool. There's no bonus points for implementing this in your assignment, sorry. I hope that you're all doing okay. Today, we're going to be working on our strings example more. It's really not going to print out much more than this char at 2 is A, but we're going to be implementing something else for that. We're going to be working on a test scaffold for that, or a test suite. There's also an example in the lecture section for lecture 14 on the course content called badcomputer.c. We will look at this a little bit later in the class. We're not going to be editing this code. It's more of a worked example that I want to use as a kind of like a case study for debugging. So by the end of today's lecture, what I want you to be able to do is implement a test harness that automates the testing of an ADT. So I really specifically want to build something up, something minimal for our strings example, so you have a solid idea of what it could look like beyond the testing a single function that we had in assignment 1. I want to do a formal treatment of make and Makefiles. So yesterday I said, hey, here's make, you can use it, please use it, please use it. But today I want to spend some time talking about build tools in general, so software that compiles other software. And I really specifically want to talk about make and Makefile, and we're going to edit to Makefile. So in terms of the learning outcomes that you have for this course, you are really only expected to be able to be given a Makefile and then edit the Makefile to work with your code. And to be really clear, in terms of the way that you'll be assessed on this, you'll be assessed on make by having a Makefile for your assignment 3, but I'm not going to ask you to write a Makefile on the final exam. That would be kind of crazy for me to do that. So we'll talk about make and Makefiles. And then the other thing I want to talk about today is to start thinking about debuggers. So I'm confident that all of you have done debugging before with Java code, at least using the Visual Studio debugger. No? Okay. Well, we're going to use a command line debugger called LLDB in this course. And part of using a command line debugger is that even though you have Visual Studio Code in front of you on your machine, you've got a full suite that can get all this stuff to work. You're going to be in circumstances where you're editing code on a remote machine. And you're going to be in that circumstance in this course, particularly if you're using a Mac where you have to compile and run your code on Aviary. The behavior that you're seeing on Aviary might be different than what you have on your Mac. So using a debugger like LLDB that works on the command line that you can invoke remotely is essential. This is also going to be essential for even people who are running Windows or Linux, just for the same kinds of reasons. The different systems that you're connecting to remotely might have different setups and libraries and all sorts of things. So we're going to talk a little bit about that. I find this topic to be pretty important, especially because we're thinking about linked structures now, and we're getting seg faults. How many times have you seen the word segmentation faults? Put 10 fingers up, and then you could start putting your toes up if you really need to, but yeah. Debuggers are helpful for when we're in that state, and so I want to make sure that we have some time to talk about that. All right, so I want to start building a test harness for string, and then I specifically want to get to the point of building a test harness and test cases for the char@. function. So what I'm going to do is pop open my terminal here. This is, again, that strings example. And what I'm going to do is I'm going to start from scratch again. We have this main.c function in this folder, but I don't want to use this main.c. This main.c is going to be like my application code that uses my strings library. I'm going to make a new program entirely that's just the test suite and nothing else. So I'm going to start by copying my template again to main test.c. And then I'm going to start editing main test.c. Main test.c is going to be a basic test harness. The first thing that I want to test with this is going to be that I can create a string. That's the very first test that I want to run. I want to have my tests be small. I want to have them be isolated. The tests that I'm going to write and the tests that we are writing for things like stacks, these are going to be testing behaviors as opposed to testing individual functions. So when you're doing things like testing push and like that you can push and pop something on a stack, you have to do like make the stack and then push something to it and then pop something off of it. And that's calling 3 different functions, but that's kind of assessing one behavior of that stack. Can I put something on and get the same thing off? So I want to start with a string by making a test that is going to just test that I can make a string at all. So I'm going to start, and I'm going to do this in a way that's not exactly the same as what we've been building the rest of our code in terms of code quality to. And in terms of test suites and test harnesses, if you look at the learning outcomes and the way you're being assessed on question 2 in the assignment, question 2 for the code doesn't or shouldn't have best practices or programming standards. Test suites are just going to be code that we're writing to exercise the code. We're not delivering this to anybody. We're not giving this to our parents to run and evaluate on our behalf. The actual stack implementation does have that, but the test suite shouldn't. So I'm not going to do forward declaration. I'm just going to write functions at the top. I'm just going to start writing functions at the top, and I'm going to keep going from there. So the thing that I want to test first is I want to test making a string. So I'm going to call this function test make string. It's going to take no arguments. I'm going to include my strings header. And all this test function is going to do is make a string and then see if I was able to make a string. So I'm going to say this, string s. I'm going to say s is equal to make string. I'm going to pass in 12. This is 12 characters long. My test here is going to be if s does not equal null, then printf pass. Able to make a string. Else, printf fail. Not able to make a string. And then at the end of my function, I'm going to call destroy string s. Last class, I said, I think it's okay for you to just exit if you fail a test case. I'm the kind of person that wants to go and check out and see what's wrong with that code. Why did it fail? How can I figure out what's going wrong with it? This time, I'm going to show you what it would look like if you were doing this counting approach. Report how many tests passed and failed at the end. I want to count how many tests passed, and I want to count how many tests failed. So I'm going to use some file scoped variables for this. You might have used this in assignment 1 if you declared the red and green colors as character pointers outside of functions. That would have been totally fine. We're going to use integers here. File scoped variables are kind of like variables that are inside of a class, but don't have, they're not inside of a method. So they're available for that whole thing to use. Yeah.
So in our implementation, our question to recall other functions in our tests. When we're testing out like test trade or test trade stack, we can call destroy stack and like or plot, which we call peak or size or whatever.
Absolutely, yes. Yes. I think for creating a stack that I probably wouldn't call anything but create and destroy, and then isolate the second thing to be, I want to know if I can push and peek, and then I want to know if I can push and pop. Those should be separate test cases. So each test case that you're writing is kind of like one isolated unit all by itself. I create the thing I need, I work with it, and then I destroy it. I create the thing I need, I work with it, and then I destroy it. So I'm going to have here two variables, int total tests, and I'm going to initialize this to 0, and int success tests. And I'm going to initialize that to 0. I can calculate how many tests failed by subtracting from total tests the number of success tests. So I don't need to have an extra one. You could, I guess, if you wanted to have that, but that's kind of up to you. So in this case here, I'm going to add total tests, success test plus plus. And at the end of this function, I'm going to say total tests plus plus. I do need to call this function in my main function. And this is basically all that my main function is going to do now. Test make string. It calls my test case. It runs my test case. I want to do print a report here, so I'm going to do that. So I'm going to say print f total tests run is %d, successful tests is %d, failed tests is %d. And then what I'm going to pass here is total tests, success tests, and total tests minus success tests. I'm going to go back up here to put this back on the screen. This is a complete test case. This is a complete test case for the function makeString. I make it, I check to see if the thing that I get back is null, and I print out a message that's appropriate for the messages, for whether or not I've succeeded in what I wanted to test. I also want to do some general cases for the char@at function. So I'm going to start a new function here, immediately below this one. Again, I'm not doing forward declarations. I don't really care to structure it that way for this test. I just want to start doing testing. So I'm going to say void test char@at general. This takes no arguments, so it's got a void argument type. I want to declare inside the test case the stuff that I need. So I want to say string s is equal to makeString, and I'm going to say my name here, and it's 8 characters long. I'm going to destroy this string at the end. It's tempting to want to just declare the string outside of all of the test cases, because you're going to do that in every single test case. Every test case is going to use a string, so it's tempting to just take that code out and put it in some common location. I'm not doing that because I don't want the outcome of one test to affect the outcome of a different test. If you're working with a stack, for example, I don't want to have pushing and popping in one test changing the behavior of a test that's some other case that I'm working on. So for each of these test cases that I'm writing here, I'm going to create a new instance of this string to work with, as opposed to using something that's been declared outside. I'm going to want to work with this as though it is a string. I want to compare this to a regular C string. So I'm going to change this slightly to be char input, and I'm going to use my name here. And I'm going to quickly go up to the top of my file, and I'm going to include string.h, so actual string.h here. I'm going to go back down to my test char@at general function. And what I'm going to pass to makeString now is input and strlen input. I don't really want to compute that in my head anymore. The char@at function returns a character. So when we're looking at our interface for a string, we get a character back from this, and it's either the null byte or the character that we've asked for to be returned. In the general cases, I'm just working with a string, and I want to just look at every character. If I call char@at on each of these indexes, I should just get the index back that I'm expecting to get back. So I'm going to declare a couple of variables here. They're both characters. One of them is called expected, and one of them is called returned. Returned is the one that I'm going to use for when I call char@at, and expected is the one that I'm going to use to say this is what I expected to get. And then I'm going to write a loop. For int I is equal to 0, I is less than strlen input, I++. And I'm going to call char_at. Returned is equal to char_at s and then I. This is the index that I'm asking for. So position 0, position 1, position 2, position 3. I'm going to say that expected is equal to input at position I. I would expect to get back, if I created this correctly, at position I in the string object that I have is the same as position I in the array that I've got. And now I've got a conditional statement. If returned is equal to expected, then I'm going to say success tests ++. I could printf in here, expected f and got f, expected r and got r, but then I'd have 8 messages that are printed out that are identical, and that's not helpful to me when I'm looking for this. If I don't get what I expected, then I'm going to say printf. I am going to printf here. Fail, did not get expected char. Expected %c got %c. I'm not going to exit here, but again, if I were doing this yesterday, I would exit. I would stop here so that I could try to figure out what's going on with char_at before other tests were run, but this is a reasonable thing to do, to just run the test and get a failure. At the end of my loop, I'm going to say that total tests is equal to plus equals, so equal to total tests plus strlen input. I've run this many test cases on that input. And then I'm going to call this function. So I've got this function called test char_at general. I'm going to call it now. Testing code is not exciting code. It is not exciting code. It is kind of like really, really basic 10-10 level stuff. It's loops, it's conditional statements. I've got a data that I'm expecting to get back. I'm getting data that I'm actually getting back from the function, and I'm just using conditional statements to test to see whether or not the thing that I expected to get back from that function is indeed actually what I got back from that function. Do we have any questions about this so far? We okay? Okay, cool. I would like to do some edge cases for char_at. So I want to ask you, what are some edge cases for char_at? When you're giving an answer here, use the notation char_at and then like double quotes. Just put the string that you think is the edge case in double quotes, and then the index, and then what you're expecting the output to be. Okay, so this one looks good. This one is passing in a string that's 5 characters long, but I'm asking for an index at 5. I'm going to say that this is a good thing to test, but this one is not an edge case because it's invalid. The index 5 is past the end of this. If I were to run this in Java, I would expect to get an array index out of bounds exception. This one is really good. This one is really good. This one is really good. And I want to explore these ones specifically in detail. This one is kind of the same as the first one. So the null byte is what I'd expect to be returned. And I think that this is true here. I would expect the null byte to be returned here because that's the way that we wrote this code. But it's outside the bounds of what we're expecting what we're expecting a valid string to be or valid indexes. This is a string output. So I think this is a space. If you wrote this, can you quickly confirm that was supposed to be a space? Maybe they're not even in the room. Oh, yes, thank you. OK, so yeah, I think this is a good one to report. This one I think is a good one to report, partly because it's going to help us see that what we're returning is actually a space. And when we're printing stuff out for especially failing test cases, one of the strategies that I want to use is that I want to wrap the value in something that's not expected to be in my input. So I'm going to go back and I'm going to change the output for our failed test case. These are all really good. So let me do that first. I'm going to go back to here, and I'm going to change this to be, I want to make sure that I see output here. So if I get a character that's a space, I will actually be able to see it. So this is me wrapping these characters in something so that I can actually see what the character is, especially if it's a space. I'm going to do the edge case tests. I'm going to do these edge case tests. So I'm going to start a new function here, void test char at edge cases. It takes no input. The first cases that I want to test, I'm going to test the space case first, test the space case first. So I need to make a string. I'm going to copy what you had there. So this is a string, and the index that we're putting in is 4. Oh, the length is going to use the same approach here. Input, strlen, input. My expected output for this case is that I want it to be the space character. So I'm going to say if char at s4 is equal to space, then success tests ++. I'm going to print out a message here, pass got a space when expecting a space from char at. Else print f fail did not get a space when I expected a space. I'm going to say total tests ++, and then I'm going to destroy the string. So that's my first test case here. Immediately after that, I'm going to make a new string. The input that I want to give it this time is that empty string case. This is an empty string. It has length 0. I'm going to use some lines here to mark where my cases are separated from each other. This is just a style choice. I'm going to ask questions about what happens if I do char at 0 on the empty string. I think our expectation was that we would get the null byte back. I'm going to quickly check out what you wrote here. I'm going to assume that these are the null byte, so two quotes right beside each other. I'm going to assume that's the null byte. If it's that, then let's say success tests plus plus printf pass. Got the null byte when getting char 0 of the empty string, index 0 of empty string. Else printf fail, did not get the null byte at index 0 of empty string. So the messages that I'm printing out here are trying to be helpful to me as the person who's testing this. I want to know what's failing about this case so that I can quickly know where to look in my source code to figure this out. I'm going to pop open another terminal here. So I'm going to leave this up here. And pane D10. Resize pane U4. I kind of want to know what Java and Python do with an empty string at index 0. So I'm going to try this. Python 3, here's an empty string, and I'm going to ask for element 0 of the empty string in Python. String index out of range. Okay. I'm going to try this in Java. JShell is basically like an interactive prompt that you can use for Java code. So it lets me run Java code on the command line. So I'm going to say .char at 0. We get a string index out of bounds exception. And I'm also going to note this specific word right here, preconditions.java, preconditions.java. That's a relevant word to this course. I tried this last night. I tried this last night before I got here, so I knew that this was going to happen. But when I thought about it more, that made sense. It makes sense that if you ask for element 0 of something that has no elements, if we're using 0-based arrays, there is no 0th element. There is no first element to something that doesn't have anything in it. So in this case, this is what I would have imagined at first to be an edge case for testing char at. This is still an edge case test data for strings in general. For strings in general, if I'm asking for the length of an empty string, I should get back 0. But for char at, this is actually an invalid test case. This is invalid data for the char at condition. This should be true, but my assumptions about what's valid for a string and for char at have changed. So I'm going to comment this out for now. And I'm going to go to strings.h. And my assumption here has changed about what I'm allowed to pass into char at. Must be greater than or equal to 0. Must be less than the string length. If S is an empty string, the index must be greater than 0. I'm going to add this not to that, but to here. If S is empty, must be greater than 0. So not greater than or equal to 0, but greater than 0. And if I take a look now at my implementation, so I'm going to look just at strings array, strings list.c. I'm going to go down to my implementation for char at. My assertions are that it must be greater than or equal to 0 and less than string length. If this is the empty string, then this part will fail because 0 is not less than 0. So that would be a false statement. So we're going to get an assertion firing here. If we're running this with these assertions enabled, we're going to have this fire. Related to this now, I'm going to go back to Mentimeter. And I'm going to move on to the next question. Why not null? Not valid, yep. Switching from language to language. Do you mean programming language? Yeah, okay, yeah. Because null is not valid to begin with, good. My parents won't know what null is, and they can't input it as a value, excellent. There's no null key on our keyboard. Because an empty string literally has no characters. My dad knows what null is. Yeah, well, my dad could beat up your dad. No way to enter null. Null is kind of weird, yes. I'm going to pop back to my code for a second. My dad works for Microsoft. Okay. Null is not a char. Okay, good. Yeah, null is silly. Yeah, null is silly. On line 169 here, we've got assert s does not equal null. When I'm running my tests, I want my tests to work for both the debug build, the one where assertions are enabled, and the one that I give to my parents. If I pass null as a test case into this, code execution will stop. I will never get past that test case because the assertion is going to say assertion failed, s is equal to null, or assertion failed, s not equal to null. If I pass null into these things as a test, we're never going to actually get to the behavior that we're trying to evaluate. So in that case, null is not a good test because we're already dealing with null before we give this to somebody else. We're dealing with null with design by contract, making sure that the values that us as programmers and coders cannot pass to the functions that we've got. So I'm going to go back to my test now. And what I'm going to say is, while the empty string here for char at isn't an edge case because it's not valid in the first place, I'm going to make sure I've got this whole thing wrapped up here. And I'm going to say that empty string is invalid data for char at. It might be valid for other cases, but it's invalid for char at. The empty string is not a test case because it's invalid, but a string that has a single character is an edge case for char at, and it is a valid test case for char at. We've got one single character. There's exactly one index that we can refer to. So here I'm going to say that this is a string of length 1. I'm going to say if char at s0 is equal to a, then test passed. Single character test. I got back the single character A when I asked for the string that consists of the letter A at index 0. Else, printf, fail. Did not get correct single character back. from one character string. All right. This is my test harness. There is really not that much going on in here. Like I said, this is very straightforward, kind of beginner level code in terms of the structures that you're using. It's more about the data that you're passing in than it is the structure that we're building up. Yes, please.
Did you destroy the string that you made?
So I'm going to make sure I destroy it here, and I'm just going to scroll up here and make sure that I destroyed it from the last case. I commented out the one where I did the empty string for charat, so I didn't need to destroy that one. But thanks for catching that. Any other questions about this? We are good? We have a good sense of where to go? Good, good, okay. So at this point, what I would like to do is open up the floor for questions about assignment 2. Yeah. How many test cases am I expecting? The test suite that I wrote was like a few hundred lines long, but again, like looking at the style of coding that I do, there's a lot of lines that have one character on them, so take that into account. There's, I think, 4 or 5 functions that you're evaluating the behavior of, so I would expect like I don't know exactly how many test cases. I don't know, but 300 to 400 lines. I don't know the number in my head, but 300 to 400 lines of code is what I've got for my test cases. But again, lots of like blanks, lots of single character lines. Yeah. Yeah.
How do we go about testing that memory was actually?
I will answer that question in 2 ways. One, that's not something I'm asking you to test for this assignment. That's not going to be any of the issues that you're going to see in my implementation of Stack. I'm going to quit this. So the question is, how do we test for making sure that memory was freed? There's a program that's installed on Aviary that's called Valgrind or Valgrind. I don't know how to pronounce this. I'm going to call it Valgrind and not Valgrind, but you can call it whatever you want. Valgrind is a program. I didn't even say it right immediately after I said that's how I'm going to say it. Valgrind is a program that will basically run your program and then watch for every time that you call malloc. And it will also watch every time that you call free. And what it prints out is how many allocations were made. So how many times you called malloc, how many times you called free, how many bytes you were using in the heap. So all of those mallocs are going to put something into the heap. And then it tells us right here at the end, all heap blocks were freed, no leaks are possible. So Valgrind is a very quick way for you to find out if you have freed everything that you allocated. It can be helpful to tell you where you did the allocation, but that's out of scope for what we're talking about right now. It's a straightforward program to run. It is installed on Aviary. It should be installed on Aviary, and you should be able to install it on your Mac. I don't know if it's installed with Xcode. You might be able to install it with Homebrew if you have that on your system. But it should definitely be installed on Aviary. Yeah. Yeah.
Related reviews. Well, I know in the header files it says it should return. Not expect to test for that either, or is that just kind of a default thing that's going to pop up?
So the question is about make stack returns null when you're out of memory, or other cases. You should check to see if you've been returned null, kind of in the same way that I've got with the strings test here. So main test, that's kind of the first thing that we're doing. Do you need to call it a bunch of times to check if it returns null? No, you don't need to do that. It's reasonable for you to call it once and see, did it actually allocate something for me? Yeah. Yeah.
Should have a separate method for destroying the nodes list. That's that, because when you destroy the stack, you need to ensure that you destroy all the nodes that go with it too. Hopefully it does. But...
So in my string function here for destroy string, we're going through and we're releasing all of the nodes that we've allocated for the list. You can write a function to release a node if you want, but including that in your destroy stack function kind of makes sense. That's logically the same thing as what you're doing. If it helps you, and if you think it helps someone reading your code later understand what's going on a little better to have that as a separate operation, then sure. Yeah, but it's not a requirement. One little tip to remember is that when you are popping from the list, when you're removing something from the head of your list or the tail or however you structured it, when you're removing something from the list with the pop operation, make sure you free that node that you have popped, because you won't have access to it anymore unless you're keeping track of something and making it quite complicated. Yeah.
For the invariant, how many factors do you have that suggest what a valid stack is?
It kind of depends on your implementation. So the question is about the invariant of a stack. The invariant of a stack is, and really the invariant of any abstract data type that we've got right now, is 100% related to the way we've implemented it. Our interface doesn't say anything about how we have implemented it. So it depends entirely on kind of like private information that you have in the implementation code. So as an example, if you have just a list and nothing else, you would want to make sure that your list ends in null, and you would want to make sure that you have a node, maybe. You probably want to have like a length attached to your stack so you know how many nodes are in it. An invariant there might then be that you have a length that is equal to 0 and head that's equal to null, or length that's longer than 0 and you have nodes in your list. Those are the kinds of things that we're thinking about for invariants. But in terms of the nodes themselves, like you can't assume that a value in a node is anything. They're just integers. So whatever you can put in an integer is a valid thing to put into push in this case. Does that make sense?
When testing something is an integer, you do that by checking the size.
So the question is, if we have to test, ultimately your question is, do I have to test what an integer is? And no, that's like going down to first primitives here. You can assume that the type system that you've got, so when you declare something as an int, it will be an integer. You can make that assumption. You don't have to go through and verify that an integer has a range and it's going to be within that. The C compiler is preventing you from putting something that's bigger than what can fit into an integer into an integer.
Okay.
Yeah. Yeah. Should we check invalid test cases? So related to null here, no, you shouldn't, because your test cases will all fail because of assertions failing when you are running your code, and you don't want that. Invalid things should be caught by your invariant. If you're trying to do something that's invalid, then your assertions should stop you from getting into that state in the first place. Edge cases, yes. So like something that's valid but is not normal to want to do. Here's one that I can give you. If you have an empty stack, its size should be 0. That's an edge case for a stack. Any other questions? Yeah. This line at the bottom here, so the question is, do we have to do this? This is not necessary. It's something that you can do if you want, but setting that value to null in that S here, if I scroll up just a little bit, in this context, the S that's on line 161 is a stack allocated argument to this function. And if I set that value to be null, it's not going to change anything in the caller. It's indicating to me, I guess, here as I'm reading this code that I shouldn't use S anymore because it's now set to null, but free is enough. I don't have to do that. One design option that you may have, you don't have control over the interface for the stack, but if you're building your own ADT, you might want to return a pointer here. And you could return null to say, yes, this was destroyed. And then someone could say that their thing is equal to destroy that thing. And then that forces it to become null later, but it's not a requirement. You've got everything to complete the assignment now. One little tip I'll give you, one last little tip I'll give you about the input strings that can be of any size is to take a look at the manual page for malloc. There's a whole family of functions that are related to malloc that are not just malloc. You can do malloc with this. You could use malloc for this, but there are other functions that will help you. Specifically, the one on the second to last, realloc, can resize something that you've dynamically allocated previously. You could just use malloc. You could do malloc and then free and make it bigger the next time, and then free and make it bigger the next time. Realloc will also give you the ability to resize something that you previously allocated. Any other questions? All right. Okay. I want to start talking about build tools. So we've gotten to a point where we're making this strings example up. This is our long-term example, and recompiling this has gotten really quite a lot more complicated than it was originally. Anytime we're making changes to either of the interface implementations that we've got to recompile those into object files. And remember, in terms of those phases of compilation, this is the part where we're asking the compiler to go up to the assembler, so emit a bunch of binary code for this, but don't try to link it into other stuff. Just produce the binary code. It doesn't run. Once you've got that, those object files, then you have to start compiling main.c and then whatever test suite that you've got with each of those outputs from above. If I want to recompile everything in the example that we've got right now, this is the set of commands that I need to run to recompile everything in the example that we've got right now. So I'm compiling these object files at the top. I'm linking my main implementation with the two object files. I'm linking my tests with the two object files. So for 4, 5 files, I've got to run 6 different commands to recompile stuff that I can begin to work with. And that's kind of okay. Like, it's frustrating to have to make a change to something and then have to recompile a bunch of different things, but it's sustainable, barely. It's something that we could reasonably do. But if we have N files, and this is an extreme example, the most current version of the Linux kernel has 58,000 C and H files in its repository. That's really quickly just going to get out of control. Linus, our friendly gentleman from the beginning of the course, doesn't sit around running this over and over and over again for all 58,000 files. As the complexity of our software increases, we've got to get a little bit of help to manage it. And the help that we're going to get for this is in the form of build tools. You are now like semi-proficient in Java. You have some experience with C. You might have done some Python. You might have done some processing before. Different languages have different tools for building software. So when I'm using this word building software, I want to make it clear that I mean compiling software to give out to someone. Building something is the same as compiling. Different languages have different build tools. Some of those languages that you might already know. With Java, there's 3 major ones. One of them is called Ant. Ant is a piece of software that will take as input an XML formatted configuration file that tells it how to compile a bunch of Java, and then it produces a jar file. Do we know what jar files are? Yeah? You've seen a jar file somewhere? Yes? Yes? 2 people have? Yes, 3 people have. Good. A jar file is like you get a bunch of class files, and you're just like zipping them all up together, and then you can give this jar file out as a library. Maven is a build and dependency management tool. So lots of people will build software in Java, and then they will give that out as libraries. Maven gives the ability to say, I'm going to write code that depends on this library. So string.java might not be enough for what you need. You want to do templating. You want to build a website with Java. And so you can depend on some library that does web stuff for Java, and Maven will download that dependency for you, add it to your class path, and then help you build a jar file to give out to somebody. If you're doing Android development, Gradle is the one that's kind of the de facto standard. De facto means like everyone's just agreed that when we do Android dev, this is what we're going to use. Java has 3 main ones that you're going to see. You will definitely see Gradle in Comp 3350 in software engineering when you get to it as a build and dependency management tool. With Python, you don't really compile Python, but pip is a tool that kind of fits into this. It helps you package a piece of code that you've written into a library and then distribute that to other people. With C, we've got Make, we've got CMake, we've got Ninja, and then this is not an exhaustive list. There's a bunch of other things that we can be looking at. We are specifically going to be looking at GNU Make in this course. GNU Make is what's installed on Linux systems, on Aviary. On Mac OS systems, you do not have GNU Make. You have BSD Make, which is what comes with Mac OS. But functionally, it's the same as what we're going to be doing for Make and Makefiles. Make is a tool that will automate figuring out what needs to be recompiled when files change. So we've got 5 files in our set of source code so far. And what we're going to describe to Make is what's required for each of those files to be compiled. So each of those things has a dependency. My list implementation of strings depends on string.h. My main.c depends on strings_list.o. It depends on this object file being created. Make is able to go through and it will build up a dependency graph. So if you're taken 2140, you've seen graphs. If you're currently taking 2140, you may have seen graphs, but you will definitely see them before the end of the course. It's building up a directed acyclic graph of dependencies between files. And the way that it does that is it looks at when was this file last changed compared to the file that I'm trying to look at right now in terms of building. We're telling Make what dependencies each file has in this configuration file that's called a Makefile. Makefiles consist of sets of rules that describe how to build a program. So we've seen this already last class, but really formally, this whole thing that we've got here, a line that starts with something, followed by a colon, followed by a list of dependencies, and then on the next line, we have a tab character. This is a literal tab character. It is not 4 spaces, it's not 2 spaces, it's not however many spaces that we would all like tabs to be. It is literally a tab character and it cannot be anything else. But when you're working with an editor like VS Code or Vim, it knows that it should put tabs there, so it's mostly fine. We put the tab character, and then we put the command that's used to create this. So this normally for us is going to be a Clang command, and the -O is going to be whatever we have on the right side, on the left side of the colon, on the left side of the colon. Each rule that we've got in a Makefile consists of 3 parts. So the target, the thing that's on the left side of the colon, the prerequisites or dependencies, the things that must exist before we can compile the thing that we're trying to compile right now, and then the recipe. This is not just 1 line, but it can be n lines, the commands that are used to generate the target that we're trying to build. I want to add the test harness that we wrote to the Makefile that we have from last class. Again, in this course, the learning outcome for you is to be able to modify a Makefile. I'm not expecting you to write this from scratch. I am giving you a Makefile. You can change it to suit the project that you've got. I want to add our test harness to the Makefile, and then I want to run Make. So I'm going to pop over here. I'm going to quit both of these editors right now. And what I'm going to do is edit my Makefile. At the top of my Makefile is something called the all target. The all target is it's a de facto standard. The very first rule that you have in a Makefile is the one that Make will build by default. This is the one that Make will run by default. All here right now depends on main list and main array. Main list and main array are defined down here as targets, and they depend on main.c and then these 2 object files. The object files depend on strings list and the array implementation. And then at the very bottom, we've got this clean rule. Clean is not a file that gets created by Make, but rather it's a target that we're allowed to run. This .phony here at the top is, I got to be really honest. It's the people that make Make doing a bad job of doing stuff 30 years ago, and then we all just have to live with the decisions that were made. I'm going to actually correct myself. It wasn't 30 years ago. It was probably more like 40 years ago. It might have even been 45 years ago. And we've all just been living with this. There were a lot of design decisions that were made with C and Make and all these tools that were kind of like in 1979, someone said, there are too many different people depending on this specific behavior. There are hundreds of people that depend on this specific behavior. And now in 2024, we're living with that decision. There are more people in this room depending on that behavior than there were in 1979. But they didn't want to make that change. And OK, I'm going off the rails here. .phony is a special rule that says The things that are after the colon here aren't files that are going to get created. They're just targets that you can run. They're not actual files. They're just targets that you can run. So I want to add a new target for my test. My test here is called main_test.c. So I'm going to call this one main test. This is the target that I have. Main test depends on main_test.c. And what this is telling Make is that if you have generated main test, but the last changed time on main_test.c is newer than that target, then you should recompile it for me. Main_test.c depends on strings list.o. I need to have a strings implementation attached to this. And the recipe to build this is going to be the same command that we've been using to compile stuff in the past. So main_test.c strings list.o. And the target here, the file name that I want to produce as output, is always going to be the same as what the target is. So one of the recipes that I have in my rule should be the one that is going to be the output of this. To make sure that this gets built, I can do two different things. One is in this directory, I can run make main test. So main test here is the name of a target. I can say to Make, I want you to make this specific target. So ignore the .c here. Make main test says, I want you to make that target that's defined on line 5. I can run this, and I'll have to fix that in a second. Or I can go up to the top, and I can add to the end of this all target main test. If I run make all by itself, make will just by default run all of the things that are defined in main test. I'm going to very quickly edit main_test.c, and that's on line 27. I'm going to add to my clean target the new thing that I've just added to all. So main test. I'm going to modify this just a little bit. I'm going to change this to be star.o. So before I had listed out each of the .o files, the asterisk here says I want to delete everything that ends with .o as a character. It's a wildcard character. I'm going to run this one more time. There's nothing to be done for all. So none of the C files have newer modified times than any of the targets that I've got. I'm going to run this command touch. We've seen this before in our first lecture or second lecture where we were touching Pokemon. I'm going to say touch strings list.c. And what this does is it modifies the last modified time to be the current time. So now it looks to Make as though this file has been changed. I'm going to run make again, and it will automatically figure out which targets it needs to recompile to be able to take the changes that I've got. This, again, is not required for assignment 2. It would be helpful for assignment 2, but it's not required for assignment 2. It will be required in assignment 3. Any questions about Make? It's a straightforward tool, I think, and it's fairly easy to use. The main problems that I have had with it in the past and that you might get caught up with, again, is that this here is a literal tab character. It's not 4 spaces, but your editors should automatically put the correct character into those locations for you. All right, and I'm going to run main test here. And I forgot to, I think I forgot to actually call that function. So I'm going to go down here, test char at edge cases. I'm going to make it again. I'm going to run it. Failed tests -1. I guess I miscounted the number of successful tests and total tests that we had. All right. So I think with that, what I want to do is I am going to skip past debugging, and I'm going to go to outcomes here. And I'm going to say that at this point, you should be able to implement a test harness that automates the testing of an ADT. You should be able to use an automated build tool such as Make, along with a predefined Makefile to build a complex project. You should also be able to modify a Makefile to suit the project that you have got. We did not do this, but we will do this tomorrow. So tomorrow we're going to focus on using LLDB to debug command line programs. That's it for today. I hope that you all have a great day, and I will see you tomorrow. Bye, everyone.